Sometimes the map of voltage as a function of distance from an object looks quite unusual because the electric field around the object is quite unusual. We can ask how much work is required to bring a charge little q from an infinitely far away, r is infinity, up to some distance capital R near a hollow charge capital Q. We can ask this if capital R is outside this ball or if it's inside the hollow ball, where the radius of the hollow ball is little a. And we can also ask what is the voltage at these various locations. We must remember that the work done is related to the integral of force dotted into distance. In this case, the force is coming from the electric field. Outside the sphere, the electric field of the sphere from the sphere looks as if it was a point charge. It is equal to k times capital Q over r squared, where r is always the distance from the center of this ball out to some location. Inside the sphere, of course, the electric field is 0. So if we compute the work is always equal to the integral of force dotted into displacement. And if we start from infinitely far away, the lower limit of integration will be infinity. And if we end at capital R, then the upper limit of integration will be capital R. This integral may be broken into two parts. If we are integrating to a point inside of the ball, then outside the ball, the force is capital F, but inside the ball, the force is 0. And so the second term in this integral represents the increments or steps we take in the region where the force is 0. This integral, as we've computed before, is k times q, the product of the two charges divided by a, and the second integral will be 0. So the voltage will equal the work divided by little q, or kq over r if r is greater than a, or just kq over little a if r is less than a. If we were to graph this, the work done would be constant if you're at a distance r inside of a, and falling off like r, 1 over r if you're at a distance r outside of a.